Hello everyone. In today's lecture we are discussing about the experiments and the findings that led to describe the atom as we know it today, and that's what we call atomic theory. So at the beginning what was found was that if you put two chemicals to react, two elements for this matter, in this case we have sodium chloride, it's formed by sodium and chlorine. If you mix them together, you will obtain a certain mass of the sodium. The point here is that whenever they do this, and let's say you started or you had 7.7 grams of sodium and you have 18.9 grams of chlorine, and you see you have a total at the beginning of 19.6 grams, then when you complete the reaction and you collect your product, you see that you still have 19.6 grams. So no matter what you start with at the beginning of that reaction, when you look at what you obtain at the end of that reaction, you see the same mass. No matter how many times you did this, you always have the same result. Whatever you put at the beginning of that reaction in terms of mass, you obtain the same mass. A different composition, yes, but you still have the same mass of material at the end of that reaction. The law of conservation of mass was first established by Antoine Lavoisier in 1789, and what it basically says is that the total mass of a system at the beginning and at the end is going to be the same. So it cannot be created, cannot be destroyed. Whatever you put at the beginning is still there at the end. Different composition again, but depending on the process, but the mass will not change. So simply put, the mass is constant during either a chemical or a physical change. It doesn't matter what you do, the mass that you obtain at the end is the same. Now if we continue with sodium chloride and we take a sample of sodium chloride and you analyze for content, you know it's sodium, there is chlorine. If you take 100 grams of sodium chloride and you analyze that, you obtain 39.3 grams of sodium and 60.7 grams of chlorine. If you divide those two masses, then you obtain a 154 ratio between those two numbers. The masses of chlorine, the ratio mass of chlorine mass to If we take a look at the proportions in sodium chloride, if you take 100 grams of sodium chloride and you analyze for content of sodium and chlorine, then you obtain that there is 39.3 grams of sodium and 60.7 grams of chlorine in sodium chloride, in that 100 grams of sodium chloride. If you take the ratio chlorine to sodium, the masses of those two, you obtain 154. Now, if you take a sample, bigger sample, let's say 200 grams of sodium chloride, and then you do the same, you have 121.4 grams of chlorine and 78.6 grams of sodium. If you divide those two, you obtain again 154. Now you do this several times, and no matter what the initial mass of sodium chloride is, you always obtain the same number. So that tells you something, and this was established as the law of definite proportion. It was first established by Joseph Prost in 1794, and it says that in a compound, a given compound, no matter how you prepare it, no matter where it comes from, if you analyze the content, if you analyze those elements that are in that compound, they are always in the same proportion. No matter how much of the compound you used, no matter where you get it from, if it's that compound, then the proportion of those two elements are going to be always the same. Now that's not exactly true or constant, but if we take a look at carbon oxides, it's carbon and oxygen. It's the same two elements, but they can react differently. Carbon and oxygen can give you carbon monoxide or carbon dioxide, two different compounds, same elements, but you have two different compounds there. If you take a look at carbon monoxide, the mass ratio oxygen to carbon is 133. And if you take a look at carbon dioxide, well, that mass ratio changes. You have a little more oxygen there. It's 267. Now, if you compare those two numbers and you take the ratio of those two numbers, 267 divided by 133, then you find that that number is a whole number. And it not only happens with carbon dioxide and carbon monoxide. Any compound that you have that have the same elements but they are in different proportions, if you do this, then you obtain a whole number, and that's what we know as the law of multiple proportions. So it was first established by John Dalton in 1804, and it says that when you have two elements, A and B, it doesn't matter which ones, and you form two different compounds, not only limited to two but more, then if you look at those mass ratios between those compounds and you divide those two, then you obtain whole numbers. So it doesn't matter how many times you do it, it doesn't matter what you use to compare those two compounds, no matter what elements, you always find the same result. That is a law. So that led Dalton to establish his postulates on atomic theory, and the first one is that matter is composed of atoms. So the atoms, the smallest particle of matter that we know, it has the same properties. If you go smaller, that's it's gonna make sense a little later, then you lose those chemical properties. So, but the atom is the smallest particle of matter that retains all the properties. Now, when you look at elements, elements consist of only one type of atom. Elements are different, elements behave differently, therefore it has to be different atoms. You look an element, a different element, those are different atoms, but atoms nonetheless. Now the fourth postulate says that compounds formed by two atoms of two or more elements, they are always do it in small whole numbers. So that small whole number ratio refers to the number of atoms that are forming that compound. And in a reaction, atoms are not destroyed or created. They are rearranged. You have a different composition. You have different properties after a reaction. But the critical thing here is that the mass remains constant. So these last two postulates, the first one has to do with the law of definite proportions. It's the basis of the law of definite proportions. And the last one has to do with the law of mass conservation. So that triggers the interest of these scientists. Well, we are talking about atoms, but what does an atom really looks like? So there were several experiments that were conducted, and we're going to discuss most of them, or the most important ones. So we have Thomson's cathode ray tube. We have the Millikan charge and mass of an electron, and then we have Rutherford here with the discovery of the nucleus, and last but not least, Chadwick with the discovery of the neutron. Those are the main experiments that led to describe the atom as we know it today. So let's start with the Thomson's cathode ray tube. And what he did was to take that glass sort of cylinder, and there was a gas there, but you see there is a negative plate there and a positive plate there, and when he applied a difference of potential between those two plates, what he saw was a beam that initially was believed to be light. So I recommend, I'm not going into too much detail into this, but there are two videos that I recommend you watch after this to get a better understanding of this experiment. The thing is, you apply that difference of potential here. And as a result, you saw that beam that initially was believed to be light. Okay, this is how it looks, but they have an interesting property. So this is when you have nothing, just the cathode ray tube. Okay, but what was interesting is that if you approach a magnet here, then you see that being supposedly light, but it bent. Okay, in this case, in the first case, it was bending away from that magnet pole, but then it was here. You also have a magnet, but still the beam is being deflected. In one case was going away from the one of the poles. You use the other pole of the magnet, and then it was getting closer to that pole. So it was repelled by one of the poles of the magnet, and it was attracted by the other pole. If you do this with an electric field, then you get the same result, meaning those particles were electrically charged. And they were attracted to the positive side. Those particles were attracted to the positive side, meaning that being has to be negatively charged. Okay? It couldn't be light because light just doesn't behave like that. So if you were able to deflect that being, that it means that being was made out of particles. Okay? So the results, those rays, they were not light, they were tiny particles. They were negatively charged because they were attracted to the positive plate if you apply a electrical field. Okay, how much they were deflected, how much they deviate from the straight path, depends on the charge and mass of those particles. It didn't matter what you use for that, you obtain the same result. So the main finding in this experiment was that the charge to mass ratio of those particles was minus, because they are negatively charged particles, 1.76 10 to the power of 11 coulombs per kilogram. You don't need to worry about that number. You don't have to memorize it. If you need it, you will be given. That's all. No need to worry about that number. So conclusions here. Yes, they are particles. The hydrogen atom was well known at the time, and that particle was 2,000 times smaller. That they get that because of the deflection they get. They compare that deflection with what happens to hydrogen. The conclusion is, well, 2,000 times smaller. It has to be pieces of atoms. So the atoms is, after all, not the smallest particle known to man. And Thomson believes these were the ultimate building blocks. So what that means is, well, they are a fundamental piece of the atom, but still the story is not complete. Because after all, if the atom is electrically neutral, but you are finding something that is negatively charged, well, there is still something else that we have to discover. So nonetheless, in this experiment, is the one that actually led to the discovery of electrons. Okay, those tiny particles that are negatively charged. So the way Thomson see the atom at the time, they use the plum pudding model, which I don't really like very much. I prefer to say that this is a chocolate chip cookie. Okay, and basically the cookie itself is the atom, and the chocolate chips are the electrons. So Thomson viewed the atom as a solid piece of matter that has to be positively charged because the matter is electrically neutral. But if you find those negatively charged particles, then they have to be there to neutralize that positive charge. Almost at the same time, because 100 years ago, a difference of 1 or 2 years was basically at the same time. Then we have a different model. Okay, the plum pudding is Thomson's. Now Nagaoka proposed this. This looks a little more like we know about the atom. So you have a center where you have the positive charge, and then you have electrons moving around. Those are negative charges. Positive and negative cancel each other. You have a neutral atom. Okay. Now Millikan's experiment. This was interesting because what he did, you have again plates. You have a positive plate there, and then you have another plate here that is negative, and he was using oil, tiny droplets of oil, and they were going through these plates. Now he used X-rays to irradiate those tiny particles, and when you do that, X-rays are ionizing radiation. They will develop a charge on those particles, and depending on the difference in potential between those two plates, then he got to see that at some point those tiny particles, those droplets, were floating in air. They were developing a charge, they floating in air because they were being repelled by the negative side and attracted by the positive side, so there was one force going up. Okay, gravity was pulling that droplet out, but the attraction and the repulsion were keeping the droplet floating. Now that didn't happen with every single droplet at a given potential. What I mean is, not all of them, if you fix the potential, not all of them will be floating. So there were ones that were floating, and there were others that were just keep dropping. But if he changed the difference in potential between those two plates, then he will find that some droplets will continue, some droplets will still float. He repeated this many times, and he observed the results that you have here in this table. Okay, so for a moment, let's just forget about the 10 to the negative 19, and you look at those numbers. You have 1.6, you have 3.2, 4.8, 6.4. Can you see a pattern there? Okay, let's start with the smallest number. It's 1.6. What's the next one? 3.2, and 3.2 is 2 times 1.6. Then you see 4.8, and 4.8 is 3 times 0.4 is 4 times 1.6. So it was always the values that he was obtaining were always a multiple of the same number. It was always a multiple of 1.6. So that led to the conclusion that, and here is another video that you should watch if you want to see an animation of this experiment, that led to the conclusion that it was a negative charge that you have there. If this is the smallest one that you can obtain, then that has to represent the charge of one electron. Now, from Thomson's experiment, you have the charge to mass ratio. With this, you have the charge. Now, you can determine what the electron mass is. So that's the importance of Millikan's experiment. He was able to determine what the charge of an electron is, and with the charge of an electron and the charge to mass ratio that Thomson obtained, then you were able to determine what the mass of the electron was. Okay. Another important discovery was the radioactive decay, and that was the natural disintegration of the atom. Okay, it was found that some elements will produce a radiation that can interact with matter. Interacting with matter means that it's ionizing radiation. It was radiation that could cause changes in matter. So initially it was thought of light, but this would happen in the dark as well. So even if you think of phosphorescence, for example, those are materials that if you put light on them and then you put it in the dark, they will be some phosphorescence there, they will produce light. But if you have a substance that has not been exposed to light and it looks dark, that process will still happen. So this process is spontaneous, and then later on it was called natural radioactivity, just because the process is spontaneous. You don't need to do anything for that process to happen. It was found later that radioactivity, it was mainly particles and energy, okay, both. And what they found is that the main particles that they found for natural radioactivity were the alpha particles, beta particles, positrons, and gamma rays. Okay, so gamma rays might sound familiar because of this little guy that we have here. Alpha particles, they were positive, and they resemble, now we know that they resemble a helium-4 nuclei. Beta particles are basically electrons. The main difference between the beta particles and an electron is just the energy. If an electron has extremely high energy, you call that a beta particle. Now the positron think in terms of an electron that is positive, not negative. Same thing, it's extremely high in energy, that's why you call it a positron. And then gamma rays is a form of light. It's a very high energy form of light. Okay, and yes, if you are exposed to gamma rays, you will not become the Hulk. You will most likely die if you have overexposure to gamma rays. So these are a summary of all those particles. There are a bunch of symbols that you can use to represent each one of those particles. I will ask you just to focus on this one. An alpha particle is just the symbol alpha from the Greek alphabet. A beta, well, there is a negatively charged electron and a positively charged electron, so focus on this one, beta minus or beta plus. Beta minus is a beta, beta plus is a positron, and for gamma rays, it's just the gamma from the Greek alphabet. Okay? So the next experiment is Rutherford's experiment, and it was important because at that point there was a lot known of radioactivity, and he was using alpha particles. We already know the alpha particles at this point are positively charged, and he was using a gold foil here. Think of an aluminum foil but made out of gold. That was what he was using, and what he found was that there were some of those particles like this that were passing through. It was like there was nothing there. Okay, we know there are particles. There are particles that you are projecting at a gold foil, and they were going through that gold foil like nothing. Like there was nothing there. You couldn't see any changes on the gold foil. It's not like they just perforated the aluminum foil. The gold foil was intact. Nothing was happening to the gold foil. So those particles were just passing through. Some of them, like this one and this one, were deflected. They were not following a straight path, so it looks like they were hitting something. So if the particles were passing like there was nothing, then there was evidence that there was empty space there. It was not all empty space. Well, at least you can see something, and if the particles were being deflected, then they must be hitting something. But the most interesting one was that there were some particles that were bouncing back. So why would they do that? So they will try to continue in motion. So it was more to bounce back from that gold foil. It means, well, there must be some repulsion there. So here is another link for an animation that I recommend you to see this experiment in motion, so to speak. Okay, but the results here is most of the particles were passing through like there was nothing. Now we have a number for that. Now about 98. It was almost all the particles were going just through. There was nothing. They were not interacting with anything on their way. So you have 2% that were deflected, so they were actually hitting something. So whatever they were hitting, it was really small, because if not, you wouldn't have that such a small percentage. However, here this is probably the most interesting result in this experiment. 0.005% of the particles were bouncing back from the gold foil, and the comparison that they make is that imagine that you are firing a 15-inch cannonball to a tissue paper, and it just bounce back to you. So that's about the energy that we are talking here, and this is alpha particles. Okay, so the conclusion that you get from this experiment, there is a tiny dense center in the atom, and we call that the nucleus. Okay, so that's the evidence for the discovery of the nucleus. It's really, really small. The atom is basically empty space. All the mass of the atom is concentrated in the nucleus. Okay, remember, the electrons are really, really tiny, so the contribution of mass from the electron is practically negligible, and is positively charged. The evidence for this is those alpha particles bouncing back. There is no reason for those particles to bounce back if they were not repelled, so the nucleus is positively charged. Okay, and the electrons are moving around that empty space. Why do you know that the electrons are moving in the empty space? The nucleus is positive. If the electrons were inside the nucleus would be neutral, and if it was neutral, the alpha particles will actually hit the nucleus and will not go back. They will not bounce back. So that's the main evidence for that. So now the view that we have of the atom looks like here, like this. Okay, and just think of that if you go to a football game and you get to stand on the 50-yard line at the Kroger Field, if you put a marble in the center of the 50-yard line, that is your nucleus, and the entire stadium would be your atom. So that's the relative size of nucleus versus size of the atom. Okay. However, the story is still not complete, because at that point a lot was known about the atom, and it was known that beryllium, for example, has 4 protons. Okay, they were able to determine what the charge of a given particle is. So 4 protons means it's 4 positive charges that you see in beryllium. Now, they are 4 positively charged particles all together in a nucleus. Shouldn't be any repulsion there. How do they stick together in that nucleus? Moreover, if you have 4 protons there, this is gonna make sense a little more later on, but it should have a mass of 4 AMUs, that's atomic mass unit. But they found that the beryllium nucleus is actually 9 AMUs. So where is that coming from? I know 4 coming from protons, but where are the other 5 coming from? The electron could not be responsible, because the electron is really tiny. The mass is insignificant. So here Rutherford proposed that there was another particle. It's neutral in nature. It was called a neutron, but you know, at that point people wanted to, okay, let's see if you are right. With the discovery of the radioactivity, it was believed that this radiation was coming from new elements, but when they were chemically analyzed, they found out that they were not new elements. They were same elements already known, but they have that different behavior. So, however, chemically, they still react the same thing. So in 1921, Frederick Soddy proposed, well, there are isotopes. It's atoms of the same element. They behave chemically, they behave exactly the same, but they have different masses. Okay, so now the question is, why do they have different masses? So it comes to the discovery of the neutron. Again, a lot of particles were known at the time, so initially what they were trying to do is use an alpha particle source like polonium, and they irradiate beryllium. And if you do that and you try to measure what's coming out of beryllium, well, you get nothing. Okay, you know there was something there, you could not detect it. That radiation was not affected by electrical or magnetic fields, which means it was neutral. And if it was neutral, they believed that they were gamma rays, but gamma rays is a form of light. However, the gamma rays cannot eject protons, for example, out of matter. So if they put this radiation, okay, if you put that paraffin here now, then you could see now that this radiation, what is coming from beryllium, is producing protons out of the paraffin. So somehow that radiation is knocking off those protons out of the matter. Now, at that time, protons were easily measurable. So at that point, any charged particle could be measured, be whether an electron, a positron, or a alpha particles. They were very easily measured. But when it comes to neutral radiation, they run into problems. So the way they have to detect this particularly was through measuring what they do when interact with matter. So that's basically how they discover, okay, this is something coming out of beryllium. It's neutral. It must have a mass, because gamma rays don't have a mass. So they cannot really interact with heavier particles. Imagine you trying to push a truck. Can you do it? No, it's too heavy. So can you push a bike? Yes, you can. You have comparable masses there. So that was the evidence for the. Now they want to discover gamma radiation. was James Sagre in 1932, and gamma radiation is not gamma rays. Okay, it's a different type of radiation. It's a neutral radiation. It's a penetrating radiation, can interact with matter, has no charge, but they are not the same as gamma rays. Gamma rays are electromagnetic radiation. Gamma radiation is basically neutrons. And with that, it was clear now that those isotopes that are atoms of the same element, they have different mass because they have a different number of neutrons. Okay, and with this our model is complete. Now we have an atom that looks like something. You have a nucleus in the center of the atom. In that nucleus you will have protons and neutrons. Okay, these are in the nucleus, and then the electron is moving around the nucleus. Okay, these are properties that you have for each one of these particles. The only thing that you really need to memorize out of this table is just that the electron, the charge of the electron, we consider that as to be -1, and the charge of the proton is +1. Anything else on this table you don't really need to memorize, but it summarizes the properties of these subatomic particles.